I've got some examples. I've got a set of examples we're going to go through to try to make this make sense. At the location marked with an X, the electric field is 2,000 newtons for each Coulomb, and it points to the right. So it points to the right. What is the electric force, size, and direction on a 6 microcoulomb charge placed at the X? So I placed that 6 microcoulombs there. It's positive 6 microcoulombs. What direction is the force going to act? What direction will the red vector point? In the same direction or the opposite direction?
Same.
In the same. If a plus 1 coulomb is going to be pushed that way, a plus 6 microcoulombs is just going to be pushed to the right. Okay? Now, if I plug in those numbers, I get a value of 1.2 times 10 to the minus 2 newtons to the right. Now, folks, these values up here in this example are typical values you would find in a laboratory. And yet my experience has been that when we use numbers like this, it becomes mathematics. It just becomes a bunch of symbols on the page. So let me revisit this example with numbers we can wrap our head around. What if the field is only 20 newtons for each coulomb? And what if instead of 6 microcoulombs, I actually have 3 coulombs? I mean, we've destroyed Bozeman, but for the sake of understanding, let's make it 3. If this field is pushing with a force of 20 newtons on each coulomb, and I have 3 coulombs, what's the total push? 60. That's all it is. That's all it is. How much are you going to pay for your tank of gas? Okay? That 20 is the rate. $20 per gallon. That's in Europe. Okay? And I want 3 gallons. Well, that'd be 3 liters. Oh, we got that. Now, what if that charge that I put there were the same size, but it was negative? What if it was negative 3 coulombs? Now, this is where some people, when they're beginning their study, struggle. If I look at this formula for the electric force, I have to remember that it's a vector formula. And if I have a vector pointing this way, let's call that vector C, and I multiply that vector by 2, well, that just makes the vector longer. I can multiply that vector by any positive number, and it'll stay pointing the same direction. It's only when I multiply it by minus 2 that I can change the direction. Now here's how this works. If that charge is minus 3 coulombs, and if that electric field is 20 newtons for each coulomb to the right, then that's going to give me 60 newtons. The coulombs cancel, and the minus sign goes with the right to give me negative right. What's negative right? Left. 2 rights don't make a wrong, but 3 lefts make a right. Just saying. Okay. So whenever you have a negative test charge, that's what we call that little charge that I put there, a test charge, the force in the electric field will always point in the opposite direction. Okay? Now, what if I put it somewhere else? What if I put that test charge over here? I don't know. It turns out the gravitational field is boring. It's the same everywhere in this room. But an electric field can change drastically from point to point. And that's why we call this little guy a test charge. Because typically what we do is we take a little charge and we move it around the room and we see how it's getting pushed. And that, plus this equation, tells me what the electric field is everywhere in the room. Okay? So my answer here is, who knows? I have to be at the x where the E is given. Second example, a charge of -5 times 10 to the minus 8, we could also call that -50 nanocoulombs, feels a force of 0.2 newtons to the right. Now it's a negative test charge, so the electric field in that location is going to point which way?
Right.
To the left. Okay? And to find the size, we would use this formula in reverse, solving for E, and we would get this value here. Now again, if I did that mathematically, I would say these are vectors. The force was 0.2 newtons to the right. This is a -5 times 10 to the minus 8 coulombs. And I want the electric field. The electric field is going to be 0.2 newtons over 5 times 10 to the minus 8 coulombs. I put the minus sign, this becomes right over the minus sign. Well, that's like dividing by -1. That's the same as minus right, which is the same as left. Okay? Now again, these numbers are realistic for the lab, but not helpful to us. What if we made that -5 coulombs and the force was 15 newtons? Well, if I had to split up those 15 newtons amongst those 5 coulombs, each coulomb is going to get a push of 15 over 5, or 3 newtons for each coulomb. 3 newtons for each coulomb. That's all it is. It's just like a rate, just like the price of gasoline. Okay? That's what we mean by electric field. Now, where does E come from? We look at this formula. The force that we're calculating is the force on this charge here. The charge that we call the test charge. Okay? The one that's actually feeling or experiencing the force. The electric field is created by all the other charges in the universe except for that one charge that we're looking at the push on. Now, it turns out because of that 1 over r squared dependency, where twice as far away as 1/4 is strong, 3 times as far away as 1/9 is strong, you don't really have to worry about all the charges in the universe. You don't even really have to worry about the charges down the hall. Just the ones close by. But this charge doesn't push on himself. This charge is the one that's being pushed. This is the Captain Kirk that's being thrown on his keister. This invisible electric field is created by the other charges, the not Captain Kirks, the Klingons, if you will. And there is no force until you put the charge there, until you put Captain Kirk in the field. Is it all coming together? Beam me up, Scotty. Okay. Now, let's get the direction down. If I have a positive source, a positive Klingon, if you will, that source is going to create an electric field over here. And that field is going to point what direction? Or do we? Remember, the electric field is the one with the waffle words. The electric field says, if I reach into my pocket, and if I pull out +1 Coulomb, and if I put it at the X, the electric field will just be how hard that 1 Coulomb is pushed. Now, if that's positive and this is positive, which direction is that plus 1 Coulomb going to be pushed?
Right.
Away. Away. And so I'm going to get an electric field away from a positive. Now, if I've got a negative source, a negative Klingon, again, the electric field is the force that would act if I pulled out a plus 1 Coulomb and put it there. Well, a plus 1 Coulomb would be attracted to that, so the field at that location would be towards a negative. And it's always going to be away from a positive and towards a negative. Now, folks, I'm going to pause right here and just tell you a little bit of history. Initially, this idea of an electric field was a gimmick. The fact that this charge here could push or pull on a charge back there through empty space was offensive to a lot of scientists. They understood how you could exert a force by pushing on something, but this thing here, pushing and pulling on that thing clear back there, that's too much like witchcraft and someone needs to be drowned. Okay? So, what they did instead is they did a two-step. Okay? They said that this charge, the source charge, changed the room. Its existence in this room changes the room, sets up a field that you can't see everywhere in the room. And then the second step of the two-step, the field pushes back there. So I didn't have to deal with this action at a distance because, hey, the field was back there and it pushed. Now it turns out that even though this thing started as a gimmick, as a convenience, we found out it was real. When you look at what radio waves are, or television waves, or light, they're all electromagnetic radiation. And we find that electromagnetic radiation is an honest-to-goodness electric field changing and creating a magnetic field, which changes and makes an electric field, and it just bootstraps itself across the empty space. It turns out we just made it up as a mathematical trick, and it turned out to be real. Who knew? Okay, that's not going to be on the test. The question is, how big is this field? We know what direction it points, but how big? Well, that's given by this formula. And notice I'm calling that Coulomb's law. Well, that's strange, because on a previous slide I called this Coulomb's law. I said the electric force was equal to K Q1 Q2 over R squared. Well, we just said that the electric field was defined by this formula. The electric force on this test charge was given by the electric field at the location of the test charge times the test charge. Now, if the electric field has a magnitude of K Q source over R squared, and I plug that up into here, what I get is that the electric force has a magnitude of, there's a K, there's a Q test, there's a Q source over R squared. Which is exactly what I had here, where Q1 is Q test and Q2 is Q source. Here, I'm talking about an action at a distance. The two are pushing on each other. Here, I've broken it up into a two-step. The source creates an electric field. The electric field pushes on the test charge. It turns out that this is the better way to think of this interaction, because we're going to find that there's different ways to create an electric field than by just having a point source. We can have a sheet of charge. We can have a bunch of sheets of charge. And so this will be the fundamental equation right here. Okay? Check that your neighbor's on the bus. Okay. That constant, 9 times 10 to the 9, will be on the front page of the exam. It's called Coulomb's constant. Now let's look at the last example. I have a 2.5 microcoulomb charge. It's placed right there. And we want to find the electric field at a point 5 centimeters to the right. Now folks, what direction is that field going to point? To the right. Okay? Now, if I plug into my formula for the electric field, there's my K value, my Coulomb's constant. There's the charge that's creating the field. There's the 5 centimeters. I've got to put it in meters and square it. And what I get is a positive 9 million newtons for each Coulomb. Now, what does that plus sign mean? To the right. However, if I had put the X over here, I might have put a minus 5 centimeters in here, but it's getting squared. I would still end up with a plus 9 million newtons for each Coulomb. So I ask again, what does the plus mean? Away. Because over here, the electric field is going to be to the left. The plus sign just means away. And indeed, if we put too much stock in this plus and minus sign with three-dimensional problems, we run into trouble. Because in 3 dimensions, I have an infinite number of directions. If I call one direction the negative direction, what do I name the infinity minus 1 directions that are left? They can't all be the positive direction. So what we do instead is when we use Coulomb's law, we use it to find the magnitude, the strength of the electric field. How big is it? Always a positive number. Always, 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 always. We never put in the sign of the charge into this formula because we're only looking for the strength. And then we use the fact that this electric field is away from a positive source and towards a negative source. Always away from a positive, always towards a negative.